Assalamu alaikum, my name is Khalid Kamaluddin. I am from Group 6 and this is our plant design project. As future engineers, we were tasked to design a simple power plant using a renewable source. Our fuel of choice was biomass. Biomass is a low-cost, renewable energy source with a near-zero carbon emission. However, its high moisture content reduces efficiency during combustion. To address this, biomass is typically dried before burning. In this study, our only main focus is the power generation side of the process. Several power plants have been around for more than 20 years, and strict plant management must be carried out to keep this equipment in good condition. It is necessary to know these assets well, their importance and criticality in the factory's operation, and have up-to-date and effective preventive maintenance plans.
The process begins with storage tank for raw material biomass, where the biomass is stored before processing. Air is compressed in compressor before being sent to the combustion chamber. Biomass will burn in combustion chamber to produce steam. The steam will drive a steam turbine, which in turn drives a generator to produce an electrical energy. Then generator will convert mechanical energy from turbine into electrical energy. Next, heat exchanger involved in transferring heat. It has lake water in and lake water out. Both are for cooling a process stream. After the steam turbine, the steam goes to a condenser where it is cooled and converted back into liquid water. The condenser uses cooling water, which is then sent to a cooling tower to dissipate heat to atmosphere. And lastly, the vacuum pump in power plant will maintain the vacuum in the condenser and increase the efficiency of the turbine.
Before moving into the calculation of the component, there are some assumptions and theory that need to be considered. Based on the explanation of PFD by my team member just now, we have noticed that our power plant cycle that consists of boiler, pump, condenser, and turbine fulfill the condition of the Rankine cycle. And based on this, some assumptions have been done that Q equals to 0 in pump, W equals to 0 in boiler or combustion chamber, Q equals to 0 in turbine, and W equals to 0 in condenser. For turbine, this is the component we've worked out. We assume that the capacity of the power generation is in 500 megawatt and it have an isentropic efficiency of 40% for the turbine. With this assumption, we get to calculate the output stream of turbine that have a value of 3372.48. We're using the formula work done actual over work done isentropic, which is also equals to enthalpy inlet minus enthalpy outlet over enthalpy inlet minus enthalpy isentropic outlet. Well, because the input stream of the turbine from combustion chamber is in superheated state, thus we can get the value of the inlet enthalpy from the table S6, which is 3807.8. Not only that, the second assumption that state the change of kinetic energy and potential energy is negligible. And with this formula, the mass flow rate with 1148.58 have been calculated. Plus, we're also using the formula of the Rankine cycle, work out equals to enthalpy in minus enthalpy out to get the value of work out. They have a value of 1088.29. And in the outlet, the steam is in a saturated mixture state. For exchanger, we are using water cooling as our research. Nuclear power plant system will also using this technique as an intermediate loop. Not only that, it will also have lower operating costs. The purpose we're using heat exchangers in our biomass power plant is to recover the heat as the heat needed to recover is greater than 5 degrees Celsius. Thus, it is extremely valuable to us to preheat it. In this component, we also made two assumptions, which is kinetic energy and potential energy is negligible and no pressure will drop during the heat exchange process. With this condition, we get to use this formula for the mass flow rate in 692.032 of lake water that we use to cool down our steam. Although the state of the steam still remains same, but the quality have been decreased, proof that it eventually changed its state to saturated liquid state. For condenser, this is a place for work in. It can help to condense the steam into saturated liquid state. And by using the formula of Rankine cycle, Q out equals to enthalpy in minus enthalpy out, this can help us to get the value of Q out that have a value of 424.06. For vacuum pump, this is a place for work in. The saturated liquid from condenser will be compressed to compressed liquid and sent to combustion chamber. By this formula, work in equals to enthalpy output minus enthalpy input. We get the value of work in, which is 21.695. For combustion chamber, Its input is from vacuum pump and output to steam turbine. This is a place that Q in enter. Thus, using formula of Q in equals to enthalpy out minus enthalpy in, we will get the Q in, which is equal to 3162.965. And the most important things is we're using the formula of thermal efficiency of the Rankine cycle. And we successfully determined that our biomass power plant have thermal efficiency for about 0.34. And according to our references, the biomass plant can driven between 12 to 67% of efficiency, and our calculation have met this limitation.
So now we'll be comparing different power plants with the biomass power plant. So in terms of power generation and efficiency, biomass power plant would have a thermal efficiency of 34%. GMA power plant, which is a coal power plant, would be at a thermal efficiency of 55.9%. And solar power generation in general would have a thermal efficiency of 15 to 22%. What's with the fluctuating range of the thermal efficiency? We'll be delving into that later. The capacity for biomass power plant will be 500 megawatt, and the capacity for GMA power plant will be 1,400 megawatt, and the capacity for solar power generation will be at 620 megawatt. The process cycle for both biomass power plant and GMA power plant uses Rankine cycle. And due to solar power generation, it's using sunlight, there will be solar photovoltaic electrical system for the process cycle. The fuel cost for biomass power plant is moderate to low, as biomass is relatively easy to come by. And for GMA power plant, the fuel cost is moderate because it is very dependent on coal price, and the coal price fluctuates a little bit. And the fuel cost for solar power generation is none because sunlight is free. So we'll be comparing the reliability and grid integration of each power generation. For biomass, the baseload is achievable as long as there's enough fuel. Baseload essentially is the maximum output desired. And for GMA power plant, again, it's achievable as well as long as there's fuel. For solar power generation, however, it's very heavily dependent on weather. Good weather, for example, sunny weather, would allow the baseload to be achieved. And on cloudy days or rainy days, it's very difficult to achieve the baseload. So for actual output against max potential, for biomass and GMA power plant, it's relatively high. For biomass, it will be 70 to 90%, and for GMA power plant, it will be 70 to 85%. Solar power generation, on the other hand, can only achieve the actual output of 15 to 30% against maximum potential. And in terms of grid flexibility, both biomass and GMA power plant provide constant output and moderate grid flexibility, as it can be easily integrated to our electrical system. But for solar power generation, it is quite inflexible because it requires a battery system to be integrated into the grid flexibility. In terms of environmental impact, as we're dealing with power generation, for biomass, the net carbon impact could be potentially neutral after the manufacturing and the operation of the power plant. If it's done well and the waste is recycled, it could be theoretically carbon neutral. For GMA power plant, as it is a coal power plant, the net carbon impact is unfortunately very high. And for solar power generation, the net carbon impact is near zero after manufacturing because sunlight, again, is free and it doesn't produce any byproducts. There are byproducts available, but they are all recyclable, such as stated below. The land use for biomass power plant is relatively high due to its efficiency, and for GMA power plant, coal power plant, is relatively low. And for solar power generation, it's quite high to achieve the required output due to its limited efficiency. In terms of waste generation, biomass generates recyclable waste, for example, ash. But for GMA power plant, which is a coal power plant, it generates toxic waste such as coal ash, arsenic, and mercury. And for solar power generation, it generates waste in the form of photovoltaic panels, which can be recyclable. So in terms of operational longevity, so biomass has a typical lifespan of 20 to 30 years. GMA power plant has a typical lifespan of 30 to 40 years. And solar power generation is expected to last 25 to 30 years, all quite long lasting. Degradation rates for all of the power generations mentioned above are quite slow to moderate. Refurbishment needs, well, basically, biomass power plant is very dependent on the boiler. Hence, the boiler needs to be updated quite constantly. In terms of GMA power plant and coal power plant, there needs to update on the scrubbers and the turbines as they are used the most often. And for solar power generation, it will be the replacement and updating of photovoltaic panels, also known as PV panels.
Some risks of biomass. While biomass is a relatively carbon emission-free fuel, it also has some risks involved with it. For example, in the pre-combustion of biomass, it can release bacteria, fungi, endotoxin, or inhalable wood dust into the air if not handled properly. There's also post-combustion hazardous pollutants like CO, NOx, SOx, and ash from the burning of the biomass fuel. Although it is not a risk, may be considered a downside. Biomass power plants require huge amounts of fuel to run properly, which may not be readily available at all times. To conclude, biomass is one of the most used fuels for power generation currently for its near zero carbon emissions. We designed a simple power plant using biomass as our main fuel, and we have achieved a thermal efficiency of 34%. While biomass has advantages like being relatively clean to other fuel sources and cheaper to maintain and moderate, it also has advantages like emitting greenhouse gases, and some types of biomass fuels produce pollutants like SOx and NOx, which requires us to handle it with great care.